Thank you for stopping by. My name is Xinfeng Liang, and I'm an assistant professor at the University of Delaware. My presentation is about the hidden upwelling systems associated with the major western boundary current in the subtropical ocean basins. This work was conducted by Dr. Fenglu Liao, myself, Dr. Yun Li, and Dr. Michael Spohr. NSF and the Sloan Foundation provide support for this study. Here's some background information about this study. We first look at the ocean vertical motions. Large-scale vertical motion in the global ocean is usually much weaker than the horizontal motions, and they are very difficult to measure directly with the current day equipment. Comparing to the horizontal motion studies, the vertical motion is much less studied. That said, based on the theoretical understanding and of the observed distribution of a variety for different tracers, nowadays we have some understanding about these ocean vertical motions. Some large scale patterns have been inferred based on theory or observation. Here are some of the well-known features. We know that strong upwelling exists along most of the eastern boundary of the subtropical ocean basin and also on the equator. The intense vertical motions, upwelling, downwellings also happen in the Southern Ocean, different latitude. Also, downwellings inside the subtropical ocean basin exist because of these economic dynamics. So we do have some understanding about the ocean vertical motions. Now let's look at the western boundary current, one of the most studied ocean processes. It's well known that the WBCs play a critical role in regulating the global climate. However, the roles of WBCs in the climate system were usually examined in terms of lateral, particularly meridional transport, as well as air-sea exchanges. The possible rules of their vertical motion were usually neglected. That being said, a few previous studies, most of which are not directly focused on the WBCs, indicate that there could be strong vertical motions in the western boundary region. Those studies include idealized or theoretical ones about wind-driven circulation, as well as buoyancy forced flows. In addition, some regional observational study and at least one global study based on ocean state estimate suggest the existence of strong vertical motions in the WBC regions. Here comes to the questions we want to explore in this study. First, are the WBC upwelling revealed in previous studies robust and universal? The second is, if so, what are the dynamical explanations for the existence of those WBC upwelling systems? The third question is, how important are those WBC upwelling systems in the vertical transport of ocean mass, property, and materials? To address the questions raised above, we will examine 6 different datasets, including 5 ocean censuses products and 1 high-resolution ocean simulation. For people who are not familiar with ocean censuses product, they are ocean products that combine ocean circulation models and a variety of ocean observational data. Different approaches can be used to combine them, or in other words, assimilate the data with the model with different ways. Those data are usually close to the raw observations and much easier to analyze. The high-resolution ocean simulation does not assimilate observations, but it includes more dynamical processes because of its high resolution. Here we focus on the overlapping period, which is between January 1992 and December 2009. The one reason we pick up this 6 product because the time we started this study, only those products directly provide vertical velocity product. Let's first look at the time averaged vertical velocity from the 6 products. Here is the result from one sample depth around 300 meters. It's clear that all the products show the strong upwelling in the Southern Ocean as well as the strong vertical motion on the equator. Those are well-known features. In addition, if look carefully, we can see that strong upwelling, which are red patches in those figures, also appear in the major western boundary current in all the 6 products. We also look at the spatial map as other depths. Some of those strong WBC upwelling can actually extend down to 1,000 meters or deeper, which we're going to see that more clearly on the next slide. We now pick up a few cross sections to look at the vertical structure of those WBC upwelling systems. This figure shows the sample sections from the 5 major subtropical western boundary current and 1 eastern boundary current. The result here are based on the echo ocean state estimate. Red means upwelling, blue stands for downwelling. We can see clearly that the intense upwelling, which can be up to 1 meter per day in the WBC regions, is co-located with the western boundary current, indicating a possible dynamical link between them. Also, those intense WBC upwelling can extend from near the surface, which is about 20 to 50 meters, to more than 1,000 meters. In some cases, it can even reach 2,000 meters. Comparing to the upwelling in the WBC region and the eastern boundary region, we can see that the eastern boundary upwelling, which is well known, but it's confined near the surface and much weaker. Then we want to examine the robustness of those vertical structures. Here we show the result of the cross sections for some of the western boundary current from not only 1 product but all the 6 products. It's quite clear that despite the differences in detailed structures, the existence of those upwelling and their vertical structures seems quite robust. And you can see here for the Gulf Stream, you can see this very strong upwelling appear in all the different products, and they all kind of vertically extended from very near surface to deep ocean. Again, those upwelling systems are weak at the surface, at the exact surface, but become quite significant from about 20 to 50 meters, clearly within the mixed layer and the eutrophic layer. So that means this upwelling can really bring up material to reach the mixed layer. So they are likely important in the exchange of ocean properties and the material between the surface and the ocean interior, and therefore could potentially important for the marine biology and chemical processes. By examining the different ocean products, we concluded that the WBC upwelling is a robust feature and likely real in the ocean. Here we try to explore the possible dynamic explanation for that. Previous studies, some of which were conducted by one of the co-authors, Dr. Michael Spohr, suggest that in high latitude of the North Atlantic, for instance, where pressure gradient exists along the boundary, there could be vertical motions. We are proposing here that the upwelling near the western boundary of the subtropical gyres could be driven by a polar wall decrease in pressure gradient along the western boundary. Basically the same mechanism as previously shown in the high latitude regions, but with the opposite direction of the pressure gradient along the boundary. Here we look at the density anomaly distribution along the major western boundary currents in the subtropical ocean basin, which are related to the pressure gradient along the boundary. Indeed, you can see here the potential density in the up 1,000 meter in the echo product increase in the polar wards direction along all the WBCs in the subtropical ocean basin. So the regions of upwelling along the western boundary of the subtropical gyres, which we show in the previous slide, are also regions of negative meridional pressure gradient along the boundary. And then we're going to see how this existence of pressure gradient along the boundary can induce this WBC upwelling. Why do the pressure gradient along the western boundary will result in upwelling? It's actually quite straightforward. We know that a large-scale motion are mostly geostrophic current, so thermal wind balance will apply to them. Then consider this sample case shown here. We choose a triangle region in the Gulf Stream here. Due to the existence of pressure gradient or density gradient along AC, which is basically the direction of the western boundary current here, the density gradient is larger along BC than along BA. According to thermal wind balance, the vertical shear of horizontal velocity will be bigger in section BC than in section AB. Then, because of the mass or volume passing in the section AB should be the same as mass passing BC. If we choose a layer in the middle, if we choose a layer in the middle, for the layer above, there need to be an upwelling to make sure both the volume conservation and thermal wind balance to be satisfied. Okay, because the existence of the vertical shear of horizontal velocity and the mass balance, you have to have a vertical motion inside the water column to make sure those two principles are going to be satisfied. Okay, and on the left side, we did a simple budget analysis, a volume budget analysis, and put numbers on there and confirming this theoretical understanding. So the existence of the pressure or density gradient along the western boundary current can explain the existence of those upwelling. We are now conducting research to study why the pressure gradient exists along the WBCs at the first place. So that's ongoing studies. We then explore the contribution of those WBC upwellings to the vertical volume transport. Here the red curves show the vertical transport of WBC upwelling, and the blue curves are related to the other regions within the same latitude band and the corresponding upwelling. We can see that the vertical volume transport by the WBC upwelling is generally of the same order of magnitude as the vertical volume transport in the rest of the subtropical ocean basin. That's within the same latitude band. In some ocean basin, the WBC upwelling actually dominates the subsurface vertical transport in the subtropical ocean basin. Specifically, upwelling in the Crucial, the Gulf Stream, and the Brazil current region dominates the net volume transport in the corresponding subtropical ocean basin within the depth range between a few hundred and about 2,000 meters. As a contrasting example, vertical volume transport in the Peruvian upwelling region is much weaker and shallower compared to the WBC upwelling. We also calculate and compare the vertical volume transport associated with the four kinds of upwelling systems: the WBCs, the eastern boundary upwelling, equatorial upwelling, and the upwelling in the Southern Ocean, with the echo product. The results here show that near the surface, the equatorial upwelling, which is a blue curve here, is a dominant process for the global oceanic vertical volume transport. However, in the subsurface, the strongest upward transport is associated with the Southern Ocean as well as the WBC regions. Between 200 and 1,000 meters, the WBC-related upwelling volume transport is generally more than a third of the volume in the Southern Ocean. So the WBC upwelling is indeed important globally, but much less studied than the other upwelling systems. Here come to the conclusions. The first, robust and intense subsurface upwelling exists in 5 major subtropical WBC systems. These upwelling systems are likely driven by the meridional pressure gradients along the western boundary of the subtropical ocean basin. The WBC upwelling system are essential yet overlooked branches of the global ocean circulation, and also the WBC upwelling intersects the oceanic eutrophic and mixed layer, and thus play important roles in ocean biological and chemical processes. Thank you very much for your time. If you have questions or comments, please feel free to contact me. This is my email. Here I also list a few papers which are very closely related to this talk. So you're also welcome to comment on that. Thank you very much. Bye.